So this is the lecture number 9. Okay. Reason of operations of MOSFET. Okay. So look at this one. Let us recap once what we have learned in the previous class, right? Let us recap. Okay. We have started using NMOS transistor and PMOS transistor, right? What is the structure of this one? You should have the gate oxide, and there is a metal gate on top of it, right? Or polysilicon as well. We can take the same thing. So what is the body here in this case? Here the body is P substrate. Okay, P type. This is a N type. But the gate is same for the both. Metal gate only. Oxide is also the same. And we have a source here, N plus, and this also N plus. But here we have to consider P plus, and this should be P plus. Okay, and this is called, we normally call it as a gate. Therefore, VG, and this is a VS. This terminal is called VD. Now this is, let me consider this is the source, and this is the gate, and this is the drain. Okay, so what is the potential that we have applied between these two? This should be negative, this should be positive. This also must be positive, right? Okay, what about this one? This is positive, this is negative, this is also negative, right? That's what we have seen yesterday, and we concluded that what is the symbol representation here? This is how the symbol representation. Okay, this arrow mark represents. This arrow mark represents whether it is a N-type transistor or P-type transistor. Okay, so the arrow mark is showing here in this way. Okay, so this is the symbolic representation of NMOS transistor and PMOS transistor. Right. What are the conclusions that we have drawn on this? When gate to source voltage, okay, is less than threshold voltage of a transistor, okay, it is actually NMOS transistor. Since it is NMOS, I'm going to write in this is TN stands for the threshold voltage of a NMOS transistor. So what we concluded this one, the transistor is said to be off. Okay, there is no enough potential between the gate and source to convert the substrate near the silicon dioxide as an inversion layer. Okay, and whereas what about this is, what about here? When VCS is greater than VTP, then the MOSFET is said to be off here in the PMOS case. Okay, because we have to apply more negative potential than that of the whatever the existing negative potential of the transistor. Okay, normally the threshold voltage of a PMOS transistor is negative. Okay, we have to apply more negative, then only it will be on. Otherwise, it will be off. Okay. Now, what about the condition for the NMOS transistors to be on? VGS is greater than VTP. So under this condition, MOSFET is said to be on. What about here in this case? When VGS is less than VTP, then the transistor is said to be on. Agreed? Okay. So if it is on, means that it has got two operations, whether it is a linear mode of operation or saturation mode of operation. Okay. We have to go and investigate that. Okay. Okay. So when we can say a transistor is said to be operated in linear, in case of NMOS, when VDS value is less than VGS minus of VTN, then MOSFET is said to be linear. Whereas here, when VDS value is greater than VCS minus of VTN, the MOSFET is said to be in saturation. Okay. So what about here then? This is opposite, right? When VCS is less than VCS, sorry. When VDS value is less than VCS minus of VTP, then it is said to be in saturation. Whereas when VDS is value is greater than VCS minus of VTP, then it is said to be linear. Okay. What is the current equation in this case? What about if it is off, means what is the current equation IDS here? Drain to source voltage, sorry, current 0. But what about here also? Here also IDS is equal to 0. What is the current equation in this case? Here IDS is a mu n Cox W by L into VGS minus of VTN into VDS minus of VDS squared divided by 2. That is what the linear equation for the NMOS transistor. What about this one? The saturation, what about this? This IDS under the saturation 1 by 2 mu n Cox W by L into VGS minus of VTN whole square. Okay, this is what we need to write. Okay, we should not forget about this kind of things. Right. Whereas what about this one? Anyone in this classroom? What about this IDS here? IDS. Minus, very good. Okay, minus mu P Cox W by L into VGS minus of VTP into VDS minus of VDS squared divided by 2. Okay, should not forget about it. Now, what about in the saturation current equation of a PMOS transistor? It is minus mu P Cox W by L into VGS minus of VTP whole square. Okay, this is how we have derived in the previous class, how these equations came into the picture also. I told you. Yes, any question? 1 by 2. Yes, I forgot to write 1 by 2. Very good. Thank you. Minus 1 by 2. Okay. Yeah. What about the what is the signs of these particular things? in the NMOS case, what is the VCS, VCS, VDS, VTN, and IDS? All are positive quantities, right? Please remember positive. Okay. If you take the difference between the gate voltage and source voltage, the difference is a positive quantity. VTN also a positive quantity. Current is also positive. What about in this case here? What about here? VCS, VDS, VTP, and IDS. All are negative quantities. All are negative quantities. So don't forget about that one, right? Okay. Now, I want, okay, do one thing. Okay. For example, if this is your MOSFET, assuming that this is your N MOSFET, okay, and assume that this is the drain, this is the source, this is the gate, okay. So what is the condition on the gate potential and source potential so that the NMOS transistor is on? What direction I can go for the gate? What direction I have to go the source so that it makes sure that this transistor is set to be on? So gate should be move for positive direction. It must be go positive direction, and it has to go the net direction. It makes sure that the transistor will be on. It should be on. Okay. Similarly, what about the PMOS transistor? So what about here is a gate, let us consider. This is the source, let us consider. This is a drain, let us consider. What about the gate here? Is it a positive direction it has to go or negative direction it has to go? Negative direction, okay? So actually it is in the positive direction. It should go in the positive direction. It should go negative direction, okay? As long as the gate will go in more and more negative, the transistor becomes saturation. Sorry, the point of the on and off case condition I'm talking about. Okay, if you go more and more gate potential for the NMOS transistor, it becomes on. If you go more and more negative for the drain for the PMOS transistor, it becomes on. Okay, that's what you have to remember in this way. Okay, please remember, always try to go for positive directions of this one and negative directions of the gate in order to say MOSFET is on or off. Okay, keeping generally, we are going to keep the sources at the fixed potential. For example, in the examination, they will ask you, I'm keep on increasing the source potential for the NMOS transistor. What it becomes? You're trying to go for the cutoff, right? That means off the transistor. That means if I try to go and increase the source value in the positive direction, for example, what will happen? We're expected to go for the negative direction. Source must be going in the negative direction. But unfortunately, you're increasing the source potential in the positive direction. What it leads to? Transistor will be cut off because VGS value becomes negative. Okay, you observe this one carefully. What is the VGS here? It's a positive quantity, right? It's a positive. That means positive means that the gate potential is always positive direction. Source potential always in the negative direction. That's what it's mean, right? VC minus of VS. Okay. I'm saying that if the VS is moving forward positive direction, what will happen? Why it is so? Because this difference becomes negative. Am I right or not? Suppose for example, VC at 5 and this is at 10 volts. VS is at 10 volts. Then what will happen? Minus 5 volts. Okay, it becomes negative. For example, it's 5 I have given, minus 10 I have given for this. Source is at a more negative side I have gone. What will happen? It's a positive quantity. That is the reason why transistor becomes on. The same thing applied to here also. Okay, don't forget about it. Okay, so this is the same thing that you can also apply to apply this drain also. Sorry, the PMOS also. For example, let us take in this way. For example, this is NMOS transistor. So drain, let us assume the drain. This is the source. This is the gate. Okay. So if I say that what is the condition or what is the option that you take if you want to say the transistor is said to be in saturation? When compared to the saturation means that we have to compare from the gate to drain. Gate or drain or gate, whatever it may be. Okay. We have to compare these two things now. Okay. Whether the MOSFET is on or off depending upon the comparison between the gate and source. Once it is on, and we have to say the comparison between the gate and drain, whether it is in saturation or linear. Are you getting the point or not? Okay. Now, can you tell me if you want to say that it is we want to operate in more saturation, then what you have to do? What is the drain? So this is also positive side. This is also positive quantity. This is also positive quantity. But what do you have to do? So it should be more positive. What we have tried? More positive than the gate. Then keeping that source is at the same potential for the input side, the left side and right side. Okay. Therefore, if the VD value is greater than VC, then it is saturation. Okay. What about here in this NMOS, PMOS transistor? What about the PMOS transistor? This is the drain. Sorry. What about this? This is the source. This is the drain. This is the gate. Let me know what you have to do if you want to make this PMOS transistor saturation more negative than gate. Okay. Therefore, since it is a negative quantity, this is also a negative quantity. We have to decrease and decrease. This is more negative. Okay. Then this becomes saturation. If you want to make this is a linear region, what you have to do then? With respect to gate, I'm talking about just use the gate terminal only. If I say that this PMOS want to be operated in linear region, gate drain I'm talking about. What should be the drain? Drain should be positive direction. We have to increase in the positive direction. Then definitely it will enter into the linear region. With respect to drain, I'm talking about. Okay. So therefore, here in this case, what you have to do here in this case, if you want to operate this one in the linear region, what you have to do? We have to decrease the gate. Okay. But if you're decreasing the gate, if you decrease the drain, then definitely it will enter into the linear region. This is the one option, right? Therefore, it is for the saturation. Therefore, VD is less than VC, then it is in saturation. Okay. So in other words, when the VC value is greater than VD, then what we can say? It is in linear. Here, gate potential is less than drain potential, then what it is say? Linear. Okay. So don't forget about this. Right. Now, the people are the more problematic while talking about the PMOS transistor because it is a negative quantity. It's a more negative and the negative minus 0.1 and minus 0.7, for example. Okay, people will feel very uncomfortable to represent something in the negative quantity, right? So people will talk all about the positive quantities only. Okay, how can we represent this negative quantities of the PMOS transistor into a positive quantity? Okay. Okay. These are all the negative quantities. So far, whatever we have seen so far is a negative quantities. Okay. Of the PMOS transistor. Now we would like to use it also in the positive quantity. How do we do it? Okay. Now let us look at this point. For example, if I say in the MOS structure, if you look at this particular one, as we have seen, this is called the gate VZ, right? And this is called the, maybe let me consider this is the source, for example, okay, VS. What is the potential difference here? So far we have seen it is a negative and this is positive. And even though we have, it is a negative and positive, we have written only we have written VCS only we have written. But what is the VGS here? A negative quantity. VGS is a negative quantity. It is a negative. How we can make it as a positive? It is nothing, but it's a negative means positive means that just you reverse it, right? The source and gate. Okay, now it becomes positive quantity. Instead of VGS, what you can write? VSC. VSC becomes a positive quantity. Like this, we can all write in terms of source. Okay, like this, we can write as a positive quantity, and VSD is also a positive quantity. Okay, VTP, what we can write it is a negative. We take a magnitude of this one. Okay, take a magnitude of the VTP, can be a positive quantity. It becomes okay. And what about the IDS here now? IST, right? Okay, it becomes IST. Now it becomes a positive quantity. Okay, when all these things are positive quantities, then the relationship also can be used as a positive quantity similar to that of NMOS transistor. Okay, let me write all this equation again. What is this equation? Okay, let me copy this one. Okay, for the sake of reduce the time. Okay, come here and keep it here. Please let me know what changes that is. Let us write here. What changes according to the VSG is something like this. What about this? VSG. What should be the greater than? Becomes less than magnitude of VTP. So it becomes now it's off. Okay, IDS is equal to 0. And what about this case? Okay, all the time VTP, whenever you see the VTP, it's the magnitude of VTP. Positive quantity only we can consider. No, I'm not going to. Okay, let us write a small thing. Okay, what is this one? VSD. What about here now? VSD, VSG, and magnitude we can take. Okay, so now what it becomes now? It becomes linear. It becomes, of course, I'm sorry, this is also wrong, right? What should be, it should be greater than. Are you getting the point or not? Okay, so now what about this one? Here also we can change is S, SD, SG, and magnitude. Okay, now it becomes saturation. Okay, now what about here? VSD. Now for the VSD, it's a positive quantity, and then we can write all these things are VSG, magnitude of VTP, VSD, VSD. Okay, now what about this? VSD is a positive quantity. Is also VSC. It's a positive one. Okay, it is similar to that of what we have seen for the NMOS case as well, right? Okay, whatever we have seen for the NMOS case, the same thing. If you are not comfortable to write everything is the negative quantities, that is also we can write in the positive quantities as well. Okay, it's up to you. Okay, whichever the way that you are comfortable, you can go and use that particular thing. I'm not insisting we have to use only this kind of thing, right? Okay. Any questions so far? Shall we go and do some kind of exercise problems? Okay, right. Hopefully, I have cleared each and every point. Okay, why it is positive, why it is negative. Okay, when it is on, when it is off, everything that I have defined clearly. Okay, let's go and do some kind of. Let us find out some region of operation of various things. Okay. Please note down if you need any help. Please let me know if you need any help. Some exercise problems will do. Okay. Find the region of operation of the following. Okay. The first question is, for example, consider that they have given in this way. We have a 2 volts here they have given. Here 1.8 volts they have given, and 2 volts given here. Assuming that the threshold voltage of PMOS NMOS transistor is 0.5. Okay, assume the threshold voltage of a PMOS transistor VTN is 0.5 and VTP is equal to minus 0.5. Okay, now let me know what is the region of operation of this transistor is all about. Which one is, first of all, which one is source, which one is drain? How do we know this is the NMOS or PMOS? Arrow mark, right? Good. It is an NMOS transistor. Now, which one is the source potential terminal? Which one is the drain potential? For NMOS transistor, drain should be at the more potential, and source should be at the low potential. Why it is so? Also, I have discussed previously, right? Okay. So this is called the drain. This is called source. Definitely, this is called a gate, undoubtedly, right? That is the second. First step is to identify whether it is NMOS or PMOS. Second step is which one is the drain, which one is the source. Okay. Now we have to go and equations that we know very well. The condition. What is the condition here? First condition, whether it is on or off, how do we know? So that is done by VGS value. So must be compared with VTN. Okay, what is the VGS value? The gate potential is at 2 and source potential is at 1.8 and threshold voltage is 0.5. Okay, now what about this one? 0.2 and this is 0.5. What is the condition here? Sorry, what is the relationship here? What is the condition here? Greater than or less than? Less than, right? Okay, so this is less than. What we should say now? It is in cutoff. Okay. We take another example. It is at 0.2 at 0 volts, and this is 2 volts. Okay. So just by applying the fixed potentials, okay, I'm not varying anything. Okay. Now what is happening to this one? What is the source and drain? This is a drain. This is a source. This is the gate. Okay, right. What is the VGS now here? VGS and VTN. Quickly. 2 here, 0.5. So what is happening here? Greater than. Okay. Now it is on. Now what is our next step? So finding the VDS, VGS minus of VTN. What is happening? VDS, this is more or less. Yeah, okay, so what is happening here now? What is the VDS here? Drain to source potential is 0.2. What is the gate to source? 2 volts minus of 0.5. Okay, next what is happening here? 0.2 is less than 1.5. Therefore, it is in, sorry, it's in linear, right? It's in linear. Agree? Okay, right. So it is a linear. Next, we take another example. So far, we are going to talk about only the region of operation. We'll come to know how to calculate the ID current equations a little bit later. Okay. Let us look at in this way. This is at, for example, 2 volts, and this is -1. This is 2.5. Okay. Then how do we know about this? What is the region of operation? Okay, which one is the source here? -1. This is the drain. This is the, okay. Okay. Now what about here is VGS? VGS is and VTN. Okay, difference between these two is 3, and this is 0.5, and therefore the transistor is on. Okay. Now if it is on means definitely we should say VTN. What is the difference here now? This is 3.5, right? What about this one? I told you 2.5. Okay, therefore it is in saturation. We just minus the PTN is saturation, right? Okay. Okay. Let us look at it in this way. E volts, 2 volts, 5 volts. If someone didn't tell you which one is the source, which one is a drain, which one is a gate, then if somebody asks you what is the region of operation of this one, what you can say? Which one is the source? 2 volts or 5 volts? 5 volts is the source. What we have learned from basics? Lower potential should be source. What is the lower potential? 2 volts or 5 volts is lower? 2 volts is a lower. That's why it is called source. What about this one then? It could be drain. What about this one then? Gate, definitely. Okay, what is the VGS now here? VGS and VTN. Gate to source potential, 1 volt. Okay, and this is 0.5. Definitely, it's greater than the transistor set to be on. What about VDS? What is the VDS? And the VCS minus of VTN. 3 volts, right? Yes, it's a 3 volts. About this, gate to source is actually 1 minus a 0.5, 0.5. Okay, definitely it is also in saturation. So according to the question that you have to say, okay, if I say, for example, okay, the same thing, for example, same thing, I'm saying that this is the source actually. This is the source. This is the drain. And this is the gate. I have given in this way. Initially, I've given in this way. Then what is the region of operation then? Source is at 5 potential and drain is at 2 volts and the gate is at 3 volts. Then it is in yeah, I given which one is the drain, which one is the source, and the potential also I have given. I'm asking you what is the region of operation of this one? Cutoff linear saturation. Which one? It is in cutoff, right? Okay. What is the condition whether which region of operation to say? VCS we have to calculate and VTN we calculate. What is the VCS here? Gate potential is at 3, source potential at 5, and this is 0.5. This is minus 2. This is 0.5, which is less than. By looking at that one, you have to say, there's a reason why I'm keep on telling you so many things, so many things, so many times. Not that for the time waste purpose. Okay. Now you tell me at this case. So everybody can say at this point, everybody can say about this. Okay. But what about this kind of scenarios will come? Okay. Next, look at this. This is minus 2. Okay. Minus 1. Minus 0.5. Okay. Now, can you please tell me which one is the, I have not mentioned that which one is the gate, which one is the drain, which one is the source. Okay. Then I have given these fixed potentials and you should say whether it is a cutoff linear saturation. This is equivalently say something like this. This is also equivalent to say like this one. Okay. If this is the circuit, if I give, then definitely you will collapse. There's a reason again. What is the meaning of this one? Okay. Then okay, keeping aside. So let me write this one. Okay. What about this? Yeah. Which one is this? It's NMOS transistor, definitely. Okay. Because why it is so all are negative quantities, but I say I'm saying the NMOS transistor because of the arrow one. Okay. Which one is the source? Which one is the drain? Initially, I didn't mention. Now you have to say me. Which one is the lowest potential? Which one is the lowest potential here? So here is the source here. Okay. This is the drain. This is the okay. So what is the potential difference here? What is the VGS now? VGS and VTN. What is this one? Gate to source potential. Gate is at -1. This is minus of minus 0.5. This is a 0.5. Amma? Source is -2. I'm sorry. Yeah. Good. Source is -2. It is -2. Okay. What about here? 1. Okay. So therefore, since I have given all these things are negative, then you should not say this is a cutoff. Since the gate is -1, you should not come to conclusion that. Okay. Now, what about this on means that which one condition we have to go? VDS and relationship VGS minus of VTN. What is the relation here now? VDS, drain is at -0.5, source is at -2. Therefore, it becomes 1.5. What about this side? 0.5. Okay. Now it is in saturation. Okay. Okay. For example, if I give something like this, copy, and then paste here. If I say this is at 0 potential, for example, it is at 0 potential. Okay. Again, I have not given anything here. Then can you please tell me which region of operation this is? Which one is the source? Which one is the drain? Source is -2 here, and this is a drain. Okay. Definitely, which region of operation? This is on actually, right? This is on transistor. Okay. What about if on means linear region or saturation? VDS we have to calculate and VGS minus of VTN. What is the VDS? VDS 2. It should be 2. What about VGS minus of VTN? Sorry. VGS is it should be 1, right? 1 minus 0.5. That is 2.5. That is greater than. It is a saturation. Okay. If I take the same thing, if I take this is a positive, for example, and this is make a positive, and this is the one. So can you please tell me what happened to this one now? Definitely it becomes drain, it becomes source. Okay. Now what is the region of operation? Cut off. Because the source is at positive side and gate is at negative side. Definitely it is in cutoff. Undoubtedly we have to, by looking at that one, we have to say it is in cutoff. Okay. Let's do some PMOS transistors.